So after creating this megalithic structure, I graduated in 2010. Here's some photos. And at that point, I moved to Sacramento. So Sacramento is kind of interesting. You've got a lot of concern about water, but most of the concern in Sacramento is about flooding, because they actually have a convergence of two different river systems. You've got the San Joaquin River system and the Sacramento River system, and they converge around Sacramento and then move out through the Sacramento Delta towards the San Francisco Bay. Now, that means that a lot of levee systems exist, a lot of water control systems exist, and a little while ago, California was into gold. And when you're mining gold, you end up creating a lot of sediment. And so essentially what ends up happening is you end up with lots and lots of silt getting into your river systems. Well, at that time, they engineered the levees to deal with this silt. Normally, if you have flooding, what happens to that silt? Well, the floodwaters rise, the water spreads out, the water slows down, and a lot of the sediment that's in suspension suddenly falls out, and so you get silt everywhere. And so it's a big problem to deal with, because the real threat is that it could change the course of your river channels. So rather than allow that, they built in their levees very close to the actual main path of water. So essentially what we're talking about is they've got very close levees, which of course, let's say if this green line represents an ideal levee distance, they've got them a lot closer to that. What that allowed was every time they had a moderate flood, the waters would rise, but they would be so close together that the velocity was maintained. So you kept velocity sufficient to allow sediment to be transferred. As the advantage of that was you dealt with the sediment in the gold days. The disadvantage is you can't handle a big flood as well, because there's nowhere for the water to go. And so you're just going to have overtop levees and so on. So now they're in the process of trying to reassess their levee systems after, we all remember, Katrina. And so the problem is we don't want to see history repeat itself. Although realistically, it's not like Sacramento is new to flooding. This type of thing has happened before. You've had parts of Sacramento 20 feet underwater. You've had levee breaks. You have various flood problems. Anyway, every year there's a constant flood fight effort going on to maintain and repair levees and fix structures. So a big part of FEMA funding that came down was learning lessons from Katrina. Let's see if we can't attack some of these problems before they become a crisis. And how do we go about doing it? So that's where my company starts getting involved. I now work for GEI Consultants, and they're just basically an engineering and consulting firm, but in our local branch, they are very water resources specialized. Their principal concern is addressing the levee systems, and their main clients are the Department of Water Resources and the Army Corps of Engineers. So in that scope, they have an idea of what they're trying to accomplish. So there's certain initiatives that have been put forward by the federal government and are funded initiatives to basically have improved flood emergency response, improved flood safety, and a whole series of steps that's going to carry on until I think 2020. And what we are doing in all of that, we're big into the emergency response and emergency planning aspect of things. And so what we're trying to do now, one of the goals is to bring together, we have GIS data. We have historical reports. These are more like real field reports, so they don't necessarily have GIS associated fields. They might be representing where they are based on some kind of a levee mile notation, or they might be representing where they are from some kind of visual, like literal description off of I-5 by so many miles. And so then you have emergency planning strategies. And what we're doing, part of what we're doing is pulling all of this information together into a single database that can be accessible on demand, real time. And that's going to bring us to the next step, which is creating disaster management software, real-time resource coordination, integrated public announcements through web services, the training and simulation tools, and integrated accounting and reimbursement tools. All of these things are somewhat available today, but they aren't coordinated. Nothing really talks to each other. So they'll have people involved in each one of these steps trying to figure out as best they can by calling other people and talking to everybody. There's no real communication coordination through these patterns. So what we're going to be doing is trying to build one continuous system that's going to drive all of this from beginning to end, so it's a lot more, it feels a lot more interconnected. So one small bit part, you said, well, what have I been doing specifically for that? Well, one small bit part of that is modeling what the rivers are going to do. One small bit part of modeling what the rivers are going to do is figuring out what the tides are doing to the river. If you can, because these are so close to the ocean, the tides actually have a significant impact on what your river levels are doing upstream. So if you can model the tide effects, the tidal effects, you can have a starting point for your predictions of what the stream water levels are going to be doing too. Most of you are familiar with the idea of tides and how the sun and moon work either together or against one another in creating different tides. You've got spring tides, you've got neap tides. Essentially, it's not a simple image. It's a complex pattern, but it's deterministic. So if you can get a handle of what the tides are doing because of the motion of the planets, it's predictable enough that you can get a very clear model all the way for a long, long distance in the future. So the first thing is you go out and you get some real observations. They start off with either a stream gauge or something else that's pulling in actual either water level or current readings. And I say current because in a lot of places you have, as the tide moves in, you have water that moves in one direction. As tide moves out, you have water that moves in the other direction. So a lot of times when you're modeling current, you're doing the same kind of, it's the exact same pattern. So you can still use the same predictive tools that were designed to predict water level rises. So if we have current as a signal, for example, sometimes it almost looks like a sinusoid. And then other times it sort of has this kind of clumped appearance. And being able to model that usually means you have to put together separate sinusoidal curves that work in coordination. Some of the first analysis for tides was way back when with Sir William Thomson. And the heat was even operating on a foundation, so this didn't come out of the middle of nowhere. There was low cost figuring out that you can take a signal and subdivide it. But he was the one that came up with the ability to do that and actually use it to predict tides. And exists, so this actually was first implemented with a machine. They didn't have, computers to run their basic process back then. So they built literal mechanical machines that would take the different cosine signals and combine them. But the mathematics of it is, very old. So it resides on the idea of superposition. If you take several different signals, you can combine them in order to either cancel out or you can, if the frequencies are different, then you can create a more complicated pattern. A lot of Fourier analysis says that, if you have enough of these signals, you can recreate any pattern. But this is just showing how some of those frequencies can combine together to perform essentially periods of constructive interference and destructive interference. And you can use that to model the time. So in an example, this is trying to match up this real data signal with a red model signal. So what it does is it goes through and finds the linear least squares best fit of that real data